Okay, YouTube, in this video on polar form equations, we're going to kind of look at how we could convert equations from polar form into rectangular form. Now, in our last video, we discussed how we could do this in the other order, how we talked about how we could go from rectangular to polar. Let's just recall very, very quickly here the relationships that exist here. We could say that some point r theta here, okay, in polar form, remember that this is giving two bits of information, how far we are from the pole or the origin out to this point, but also in what direction we're headed here. And we could say that this is some objectively positive angle here, theta. And then so we could say that in rectangular form, which is what we want to go to, we could see that we would have been given some x and some y here. And so the relationships that exist between x, y, and r, let's go ahead and carefully relist these here. We'd say x squared plus y squared is equal to r squared is one primary and fundamental relationship between x and y and r. And so here's what we're going to be doing in this video. Our ambition is going to be to rewrite things in terms of r's and thetas in terms of x's and y's. And so one thing that I want everybody to look out for is the fact that we could rewrite r squared as x's and y's by replacing it with x squared plus y squared. Likewise, let's go ahead and write another relationship that we see here that relates theta to y and x, but we've seen that our tangent of our theta is equal to y over x here. And so if we know theta, then we can take the tangent of it and we could get this expression that we know would be equal to y over x. And so what I want to do is look at how we can use these two relationships in this video to help us rewrite these in terms of x's and y's instead of r's and thetas. So looking at what we have here in this first example, we would say converting this polar form equation r equals 4, which if you remember from our last video would just be all of the points having a radius value of 4 here or an r value of 4, so some circle with a radius of 4. We should get an equation that looks like a circle. In terms of circles, we have x squared plus y squared if it's centered at the origin, and because the radius is 4 here, my guess is that we get a 16 here. And so I could say that truly, yes, I know equations in rectangular form, but now let's talk about how I would have gotten this algebraically if I don't know my stuff to begin with. So we say r equals 4. Let's remember that our relationships that we have over here that relate r and theta to y and x are these. And so if we want to relate r to x and y, then perhaps what we need to be doing here is this, getting an r squared so that we can replace it with x squared plus y squared. And so that's precisely what we're going to do here. We're going to take both sides of this equation and we're going to square it out. And so we end up with this expression here, or this equation here that says r squared equals 4, oops, sorry, not 4, but 4 squared, so 16. But at the same time, we're seeing that we can make a substitution here. We could substitute in the value x squared plus y squared because we have an r squared value. And so our rectangular form equation is just easily put, this one that you see right here. Now when you look at letter B, we'd say pi thirds is our angle, and this is a polar form equation. Interestingly, these are the only types of equations you see here that aren't r equals something, but we'd say that theta equals pi thirds. This is unique in saying that we are graphing all of the points that have an angle of pi thirds. So in other words, we're graphing the equation of this line right here where pi thirds is the angle that it's headed in. So if we're going to convert this back into, rectangular form, you can see that theta is clearly related to y and x up here with this relationship here. And so what we're going to write is this. We're going to say, well, first of all, the tangent of theta is y over x. And we know what our theta value is. So we're going to make a substitution here. Substitute this pi thirds value here. So we have substitute, and then we're going to say that, well, then we know that in this particular case, this has to be the truth. So pi thirds. So here's what I'm going to tell you to do every time. If you can, and we can use a calculator to do this, of course, but we'd say evaluate this. Then we'd say tangent at pi thirds, which is really the tangent of a 60, I happen to know is equal to the square root of 3 here. So we really get y over x is equal to the square root of 3, and by taking both sides of this equation times x, what we end up with is the x's canceling out, and we get a familiar equation here, or an equation that is in a much more familiar form, this y equals mx plus b form. So we have y equals the square root of 3 times x. So this would be a line that has a y-intercept of 0, which we can clearly see up here in this picture, and a slope of the square root of 3. So it would go up the square root of 3 over 1. Excuse me. So in this last example here, this should be letter C, but we'd say we have r equals 4 sine theta here. And so because this is what we have, again, we say how could we relate r to x's and If we look at this example right here, we see r equals 4 sine theta. We want to rewrite this in terms of x's and y's as well. And so what I'm going to tell you is from time to time, because so strongly we see this relationship between x squared plus y squared equaling r squared, we want to have an r squared. And so you might think, how can I get an r squared? Well, one way to do it is to square both sides. But I'm going to tell you that this is kind of like a special instance here. So we're going to see a lot of r equals 4 sine theta, r equals some number sine theta, some number cosine theta. But what I want you to know is when you see something like this and you want to go back into rectangular form, the method is going to be this. We're going to multiply both sides by r. So multiply both sides by r. Now what I want you to see is that you still get an r squared on the left. So we would say that if we do this here, we have 4 sine theta on the right. Let's take both the right side and the left side times r. So I'm going to take this times an r, take this times an r, and I'm going to do a little bit of rewriting here, but I'm going to call this 4r sine of theta. Now, the reason why I chose to multiply through by an r is because, well, first of all, had we squared both sides, we'd have an r squared on the left. And no matter how you look at it, if you squared it or multiplied both sides by r, you can substitute in an x squared plus y squared for your r squared. That's one of our relationships over here. But also, let's remember this. From our last video, that x is equal to r cosine of theta, and that y is equal to r the sine of theta. And this just comes about by saying that our sine value is y over r, of course. You know, sine is y over r, and cosine is x over r. Then we could see that y equals r sine theta and x equals r cosine theta. So with this being said, what I see right here is an r sine theta, and that's really convenient because I know that r sine theta is the same thing as x. So we could say that this is the same thing as 4y right here, but you know, just as a general, you know, kind of thing we do with equations, let's go ahead and subtract, you know, everything off of one side here and get this into what we call general form. That is, everybody in one side equal to 0 on the right there, but we get x squared plus y squared minus 4y would be the rectangular form of the equation of this line. Cheers.